Hi everyone, we are going to talk about hierarchical clustering today. Again, it's a method for unsupervised learning. So we talked about unsupervised learning in terms of clustering. The general idea is to use past data such as customer data to create segments and clusters or groups or subgroups in your data, so that we can use these clusters to predict where future data belongs. For example, if we can segment data, customer behavior based on past history, then we can predict what a new customer is going to do. So we talked about PCA, principal components analysis. We have also talked about k-means clustering. Today we'll focus on hierarchical clustering. Again, as a review, clustering is an unsupervised learning method. There are no Y labels available. The goal is to discover structure or groupings in data. The goal is not to predict a Y label or Y value. Examples include discover similar products, identify similar reviews, group similar transactions if you're an accountant, or find distinct market segmentation. We have talked about k-means clustering, and that is about dividing data into key non-overlapping clusters. We do that by minimizing distances of cluster centroids to data. There's one problem with k-means clustering, which is we have to pick the value of k a priori, meaning ahead of time. So if you have to determine this number before you even run the analysis, so that can be a little tricky and very subjective. Although you can try different, values of k and then sort of cross-validate and try to pick the best k that way. But still, sometimes we just don't really have a way to figure out what k we want. So today we'll talk about an alternative, which is called hierarchical clustering. So the nice thing about hierarchical clustering is that there's no need to specify k a priori. So you can actually pick k, but you will do that after the analysis. So that's very nice. There are two options available. You can build a hierarchical clustering tree. So the method builds a tree. So it's easy to confuse hierarchical clustering with tree methods. I would challenge you to think about the differences. Well, they actually have nothing in common, but if anybody mentions tree versus hierarchical clustering, hopefully you will be able to explain the differences confidently. The tree is built from the bottom up. There's a big word, a fancy word for this method. It's called agglomerative. It's just a fancy word for saying that the tree grows from the bottom up. You can also build a hierarchical clustering model using a top-down method, or it's called divisive. But we're not going to talk about that in this presentation. We'll focus on the bottom-up method, which is the most common method and also is very intuitive. The method of hierarchical clustering, the key point of that is to build a dendrogram. The algorithm, of course, does all the mathematics, but the dendrogram is just a really easy way to understand the algorithm. So we're going to talk about the algorithm using a dendrogram. So again, as a reminder, we are going to focus on the method of bottom-up hierarchical clustering, meaning that we start from the bottom, which is actually the individual observations or your individual data values. And then we start to see similarities among them and we try to group them together. Okay, so because the algorithm is very easy to understand, if we look at the dendrogram, we are going to start talking about the algorithm by looking at the dendrogram. Okay. So the dendrogram, here's an example from your textbook. You can see that this is a very simple data set with only 9 observations, meaning sample size n equals 9. If you look at a data frame, there will be only 9 records or 9 rows in your data frame. Each of those data points or each row is actually represented as a leaf, right? So at the bottom, the leaves are data points. And I want you to think about how that's very different from a tree. So I want you to think about what the leaves represent in a decision tree, right? So they are not data points. What are they? Similar leaves are fused together with branches, and branches will fuse with similar branches or leaves. And so what happens is that if you look at data point 1 and data point 6, they're grouped together because they're very similar to each other. 5 and 7 are also grouped together because they're the most similar together. So we'll do like sort of 2 at a time, right? So you basically do a pairwise kind of grouping. And we find the most similar ones, we put them together, and then we group them with the next most similar data point, and so on and so forth. Okay? So you can actually see, because everything is calculated, the grouping is all based on similarity between data points. We actually have, the algorithm actually calculates how similar, how dissimilar all the data points are. So we call this the dissimilarity score or measure. On the y-axis, it measures the difference between the 2 leaves or branches. So you see the ones at the bottom, they're the most dissimilar, meaning they're the most similar, right? So this is sort of a tongue twister. You kind of want to think about how 1 and 6 score very low on dissimilarity, right? So they're very at the bottom of the scale. The measures are very short along the y-axis, and that means if you score very low on the dissimilarity score, that means that you are very similar, right? So those 2 things are kind of, the lower the number, the more similar you are, basically. The higher the number, the score, the more dissimilar things are, okay? So the most similar numbers get grouped together, and then they get grouped together with the next available one, and so on and so forth. Okay, so again, we start at the bottom. All the data points are actually at the bottom. They are all their own leaves, and then we kind of group them together into branches and so on. Okay. So how is this dendrogram constructed? Well, so first of all, the algorithm will measure the similarity or dissimilarity scores for all possible pairs. So you do a pairwise calculation. The algorithm will go through all possible pairs, right, and give every pair a score. So for example, the pair between the pair 5 and 7, they will get a similarity or dissimilarity score. Another pair, say 3 and 4, will get a dissimilarity score, and 3 and 9 will get a dissimilarity score, right? So you will just calculate all possible scores, and then you sort them from the smallest to the largest. And the smallest here is between 5 and 7, and they will use the smallest scores to construct the bottom of the tree. And then we calculate the similarity score between 5 and 7 and all other possible values, right? So we can do 5 and 7 as group, and the difference, the distance between that and 8, or we can look at the 5-7 group and the distance between that and 9, and so on and so forth. Again, you will go through all possible pairs, and then you will decide that 8 is the closest to the 5-7 pair, and then we'll put them as the next branch. Okay, and you go through this iteratively using the computer, and then the algorithm will produce the entire, map out the entire sort of structure of similarity for us, right? So the next one is 2, then the next closest one is 9, and so on and so forth. Okay. So again, to summarize, Dendrogram visualizes similarity between data points, and we do that from the ground up. And the y-axis, the values tell us how similar the data points are. Okay, so this is a very similar pair, so 1 and 6, 5 and 7. So you can see their similarity score is about 0.3. So it's a very low number. And when two pairs are very different, they will get a much bigger number for dissimilarity, right? So at about 1.8 is where 9 is different from 2, 9 is different, also different from 8 at about 1.8, 9 is different from 5 at about 1.8, and so on and so forth. Okay, so the trick is that you really shouldn't be looking at the size of the lines on the graph. The lines only stops at the data values, but really the difference is actually the entire sort of from 0 all the way up. So you really have to look at the score on the left-hand side to determine how dissimilar it is. Okay, so you should never interpret similarity horizontally, actually. So you shouldn't say that 3 is next to 4, so 3 is more similar to 4 than 1 and 6. Okay, similarly, you should not say 9 is more similar to 2, 9 is less similar to 8, 5, and 7, because that is not true. We only want to look at the number vertically. So if it's 9 is standing at 1.8, that means it's 1.8 different from 2, 8, 5, 7. It's all equal dissimilarity. It's a little tricky. So you can actually, these different cuts actually will determine how many clusters you will be. If you do the lower cut, you will get more clusters. If you get the upper cuts, you will get fewer clusters. I think I have another slide for this. But there is actually a command called cut tree, and you can tell the algorithm how many clusters you want. So if I want 2 clusters, the algorithm will do the upper cut, right? So, but if you want more, the cut will go lower and lower. So the height of the cut really determines the number of clusters. So if we look at this example over here on the left-hand side, if we do the cut at 9, okay, so you will actually get 2 clusters. So basically you do the cut and you see how many sort of branches the cut goes through, and that's how we know how many clusters there are. The clusters actually color in 2 different colors, red and green. And so those are the 2 clusters we have if we do the cut at 9. Now, if we do a cut at a similarity score of 5, then we will get 3 cuts. So this is the algorithm from your book. This is the formal write-up of it, but the idea is really simple. The first one is just take a measurement, a similarity measure between all possible pairs. And then we just go through all of them. We start with the smallest and all the way up to the least similar pairs. And then we group them accordingly. Now, the measure of the distances between 2 different points, that we actually have a lot of different options for that measure. So we'll look at all the different, some examples. There are many, many different ways to measure distances between 2 points, and so you might want to think about what you want to use. So to run the hierarchical clustering algorithm in R, we'll be using the hclust command, and then we'll talk about the different parameter settings. Okay, so one very important decision to make is how you measure the similarity between groups. So this group and this group, how do I measure how different they are? Because I'm not just clustering individual scores. I'm actually I have to, once I have small groups, then I have to lump them together into bigger groups and bigger groups. So when I do that, I have to find a way to measure the difference between 2 groups or between a group and a data point. So how do I do that? There are many different options, so let's look at the options here. So dissimilarity is basically the distance between the two groups, right? So there are many different ways to measure that because, as you can see, each group actually has multiple data points. So we can actually, we have many different ways to measure how these two groups are different. This is what we call linkage methods. So the different options for linkage methods are complete, single, average, and centroid. They will actually produce different clustering dendrograms, different results, and they have different mathematical implications. So, and for different kinds of data sets, you may want to try different linkages. So it's really, as an analyst, this is sort of part of your job is to pick out the appropriate linkage method or to try different linkage methods. So the method is specified very easily using the method parameter in the HCLust command. So you can see complete is method complete, single is method single, average is method average, and centroid is method centroid. So very straightforward. But what are the different, they're easy to actually execute and are, but what are the different measures? So let's look at that. So the first one is called complete. Okay, complete is really just looking at the two different groups, and then we'll find all possible distances between the two groups. So I will take 3 and I'll measure the distance of 3 and 7, 3 and 8, 3 and 5, 3 and 2, 1 and 2, 1 and 8, 1 and 7, 1 and 5. And you would do the same thing with 6 with all the other green dots and 4 with all the other green dots. So you will end up with all of these distances. And what you do is you use the largest score to represent the dissimilarity between the two groups. And that would be what we call the complete linkage method. Single is, on the other hand, is using the smallest dissimilarity score between all possible pairs. So again, the algorithm will calculate all possible distances and use the smallest one to represent the group difference. And that's what we call the single method. The average method will take all the dissimilarity measures, the distances, and then run the average and use that to represent the group difference. Centroid is very different, actually. So centroid will require finding the centroid of each of the groups. So you don't actually do all possible pairs anymore. So you will find the centroid for each of the clusters and then measure the distance between the two. Now, how do you find centroid? Well, centroid is the average for all the data points. Okay, so these different linkage methods will actually produce different dendrograms. So you can see average produces a tree or a dendrogram that's pretty balanced. And then you can see the complete linkage produces shape that's a little different. Single gives you a very kind of a bizarre and very skewed dendrogram. So you probably want to try different things and see which one produces the result that you're looking for. And it really depends on whether you're doing a marketing or sales or finance or genomics analysis. You may actually want very different linkage methods because you have different outcomes, so you're trying to optimize. Be careful with the centroid method. The centroid method is known to produce inversion. Inversion is the idea that two clusters are fused at a height that's below either of the individual clusters in the dendrogram. What does that mean? So if you look at the dendrogram, the data points on the left-hand side, we want to group, the algorithm may group D1 and D2, these two data points together first, and that is fused together as similarity score or dissimilarity score of 4, right? So on this right-hand side of the dendrogram. And then after that, D1 and D2, this group, then should be clustered together with D3. And when you do that, the dendrogram should grow up But here we see that the dendrogram actually inverses by going down. So the fusion actually happened at 3.5, which is bizarre. So when you have a bizarre dendrogram like that grows downward, you want to be careful because that means the algorithm is probably not working properly. Okay. There are also, like I said, there are many different ways to measure the similarity or dissimilarity between 2 points. The most common is Euclidean distances. So that's really just, taking a ruler and measure the distance between 2 points. However, there are also other options. For example, the Manhattan distance or correlation-based distance. These distances will actually have different methods that we can, our command that we can use. So the DIST command for distribution will actually calculate a matrix of distance measures. Okay, for the matrix X. Okay, so by default, the method is Euclidean. And so if you don't specify anything, like what your textbook does, then you get the Euclidean distance matrix. However, if you could say method equal Manhattan, then you will get the Manhattan distance. To get the correlation distances, you will use a slightly different command called as.dist. So let's look at each of these. So I'm not going to talk about Euclidean because that's very straightforward. Euclidean is actually the green line over here. So basically the straight line between 2 dots. Okay, so that's the shortest path. However, you can also measure Manhattan distance. So it's called Manhattan because this is how the city of Manhattan, the city of New York, is actually sort of a grid, right? So if you're a taxi cab, you usually cannot drive the distance like the green line. So instead, you probably have to take the red path, okay? Or you can take the blue path, or you can take the yellow path. As a taxi cab driver, you have these different options. The nice thing is no matter what option you take, the distance is the same from point A to point B. So red, blue, or yellow, these they actually all add up. If you do the calculation, they'll add up to be exactly the same distance. And that distance is what we call Manhattan distance. So you can produce a Manhattan distance matrix very simply by using DIST command, specifying the Manhattan method. So the idea is that if you look at this, the green, the square, actually, if you think about the square value of the green line is actually equal to the square value of the red line, right? So the rise and the line across, you can actually see the triangle, right? And so the Manhattan distance can be actually very easily calculated. But it's a longer, a much larger value than the Euclidean distance. Sometimes, especially in marketing, you probably want to use correlation-based versus Euclidean-based distances. And here's an example. So if you have 3 different customers, they are called observation 1, observation 2, and observation 3. So these are 3 rows in your data frame. And these 3 customers, if you look at customers 1 and 3, they're actually very close to each other in distance because they're very similar. The values are very similar to each other. Maybe they spend very similar amount of money. Maybe they come in at very similar times, and maybe they buy very similar. Maybe they buy very similar items. Their scores are very close to each other, no matter what you measure. And there are actually 20 different variables we measure these 2 customers on. And these values are very similar. They're both on the low end. Maybe they're both like budget shoppers and they spend very little amount of money. So they are more similar in Euclidean distances, but for these 20 different variables. So not just the amount of money they spend, but also on many other measures, right? However, if you look at customers 1 and 2, you will see that they're actually more correlated, meaning that their trends, they kind of track each other. So when the values go down for customer 2, the value also goes down for customer 1. When the value rises, in customer 2, the value also rises in customer 1. So they track each other more closely in terms of patterns, even though they are more different from each other in terms of Euclidean distances. So sometimes you want to group your customers that way instead of relying on Euclidean distances. So what you can do is you can specify a correlation matrix between the customers, and using this as.distribution.dist, 1 minus correlation of the X matrix you want to transpose at first. So basically, this is you can produce this correlation matrix and you feed that into your hierarchical clustering command as the distance matrix. Okay. Some important notes about hierarchical clustering. It's different from k-means clustering in many different ways, and we've talked about the benefit. We don't have to specify the value k ahead of time. You actually pick the number of clusters afterwards. However, hierarchical assumes that the clusters are nested, meaning that you have to group the smaller ones and then they become bigger and bigger. But clusters are not always nested. In some situations, you actually don't want nested clusters because you know something about your data set and you just know that those clusters don't make any sense. So in those cases, maybe you want to try k-means instead. The clusters like k-means clustering, so this is like a symptom for all clustering methods and not just hierarchical, but hierarchical clustering suffers from these issues. So they're not always very robust. You try different method, we already see that, right? So you try the different linkage method, you get different clustering structures. So it can drive some people crazy because there's no sort of stable solution and it's very sensitive to outliers and it produces different clusters with different subsets of data. So you try, you eliminate some data points, you add some other data points, then your cluster tree becomes wildly different. And that is an issue with clustering. So it really is an art and a science, and you really have to be very savvy in terms of picking your clusters. Clustering, just like decision trees, can overfit. So you may do lots and lots of clusters. Eventually, you have all singletons in your clusters, right? So if you have cut the dendrogram very low, you'll get lots and lots of singletons, and that's really not good. You do not want to have single data points in clusters. Then that model has no predictive power. Data should be centered and scaled because, again, clustering is very sensitive to scaling. So try to do that before you run your model. And again, there's no correct solution. So it's really a subjective decision. And as an analyst, you have to really evaluate pros and cons and pick a clustering method subjectively. And you need to be, as long as you can justify your choices, you'll be fine. So the bottom line is that you should always try different parameter settings, different subsets of data, so that these are what we call robustness checks. You try different things, different number clusters, different ways to cut, different methods, different distance measures, so that you can make sure that your model is as robust as possible. So that's all. Thank you very much.